Hello and welcome to 2022 NUS Virtual PhDShow. I'm Shitong and my PhD research topic is expansion of consistent particle method or CPM to solve solid mechanics problems. So what is CPM? Why CPM should be expanded to the area of solid mechanics and how to achieve the expansion? Well, let's find the answers in this video of my thesis. The main numerical methods for solid mechanics are mesh-based methods, for example, the finite element method or FEM, but mesh distortion has to be treated for large deformation problems. To avoid this, kernel-based particle methods without mesh were proposed, for example, the smooth particle hydrodynamics or SPH method, but non-unique user-defined kernel function and empirical artificial stabilization terms are often required, which can influence the computation results. A relatively new Lagrangian particle method, the consistent particle method or CPM, was proposed for fluid dynamics problems. The method solves Navier-Stokes equations using a predictor-corrector scheme, and the spatial derivatives of variables are computed by Taylor series expansion. CPM is suitable for solving large deformation problems in nature. Kernel function and artificial stabilization terms are now used. Before this study, CPM is only developed for solving fluid dynamics problems. Considering its meshless nature, which is potentially useful for large deformation solid mechanics problems, the objective of the PhD thesis is to expand CPM to solve solid mechanics problems. As my interest is in geotechnical engineering, the emphasis is on computational geomechanics. To achieve this objective, CPM is developed to solve 1D and 2D linear elastic as well as 2D elastoplastic problems. Subsequently, CPM is applied to solve 2D geomechanics problems. So how does CPM solve solid mechanics problems? The methodology is as follows. The governing equations are mass conservation equation and dynamic or momentum equation. The Euler trapezoidal predictor-corrector method is used as the time-stepping scheme. The spatial derivatives of variables are computed by Taylor series expansion. The expansion of a differentiable function f about a reference point I can be written in the equation here. Applying Taylor series to a sufficient number of neighbor particles within an inference radius of the reference particle I, we can get a set of linear equations, solving which the spatial derivatives at I can be obtained. The stress increments are directly computed using the constitutive relations for solids. For boundary conditions, generally the stress and velocity conditions are directly assigned to boundary particles. Under patch load, the inverse distance weighting method is applied to tackle stress singularity. No additional particles are needed to assign the boundary conditions. In large deformation problems, two simple schemes of particle repositioning and removal are proposed to preempt highly irregular particle distribution. To demonstrate the capability of CPM in solving solid mechanics problems, a series of numerical examples are studied, involving linear elastic and elastoplastic problems from small to large deformation. Due to the time limitation, only two representative examples will be shown in the following slides, which are a rod under compressive stress and footing penetration in undrained clay. To verify the feasibility of the proposed methodology, 1D shockwave propagation in a linear elastic metal rod under compressive stress is studied. The rod is fixed at the right end and loaded at the left end. A direct comparison with SPH analysis is done. The figures show the time history of stress magnitude at the fixed end obtained using SPH and CPM respectively. It should be noted that using the same number of particles as SPH with artificial viscosity, the CPM results without any damping is closer to the analytical solution, demonstrating the stability and accuracy of CPM. The second example is penetration of a plane strain rigid rough strip footing in undrained soil, involving large deformation. The soil is treated as von Mises material, and the top surface is loaded by the strip footing. Due to symmetry, only the red half is simulated. The particle repositioning scheme is applied in this large deformation problem. Compared with the FEM and particle FEM results, the Bayesian curve using CPM is the closest to the analytical solution using the slip line theory. Here, the line figure shows the particle distributions before and after the penetration, presenting the soil deformation. The figure in the middle shows the soil profile near the top boundary obtained by CPM is similar to those obtained by FEM implicit analysis and coupled Eulerian Lagrangian approach. The red figure is the vertical stress contour by CPM. The largest compressive stress happens near the edge of footing. The oscillation of stress results is due to the use of explicit dynamic analysis, and no smoothing technique is used in plotting the figure. In conclusion, from linear elastic problems with small deformation to elastoplastic problems with large deformation, CPM has been successfully expanded into the solid mechanics domain. In the future, large deformation geomechanics problems such as slope failure and mud flow will be studied to predict geohazards for a safer living environment. Thanks for listening. If you are interested or there's any question, please contact me by clicking the Drop Me a Message button at the bottom of my boot page. Thank you.